Building an AI agent that works in a demo is easy. The environment is perfectly controlled. But push that same agent out to thousands of users, day after day, and the system starts flashing red. The real engineering happens long after you prove a model can answer a question. The actual challenge is keeping the agent's memory and logic stable across thousands of continuous interactions over time. Autonomous systems do not maintain themselves. Without active state management, they fail through entirely deterministic patterns. Surviving production requires engineering specific mitigations against the specific failure modes that degrade agent quality over time. And because these agents possess autonomy, the ability to act, decide, and access data without human review, they must be fenced in by a strict zero-trust security architecture. Anyone can string together a working demo. Engineering the boundaries that keep an autonomous agent sane, secure, and reliable is where the real work begins. This visual represents a model's token window. As a conversation grows, retrieved documents, chat history, and tool outputs pile up inside it. This is context overflow. When this container gets full, the model silently truncates information, delivering answers based on incomplete data. To stop this, you implement a strict token budget, track usage, and trigger compaction the moment capacity reaches 70%. But compaction introduces catastrophic forgetting. As context is summarized, the model strips away crucial constraints the user stated initially. You fix this with importance scoring. High-value facts receive a high score. When the press activates, these protected blocks bypass compression entirely. They survive the summary. Even protected memories degrade. In context rot, an agent confidently uses a deprecated API or outdated user preference simply because the semantic memory has no mechanism to detect staleness. This diagram shows the mitigation, a time to live, or TTL tag. Every stored fact gets an expiration timer. Technical facts might get 30 days. User preferences get 90. When that timer hits 0, the memory receives a low confidence flag. The system must then act on that expired tag. It either explicitly asks the user to re-verify the fact, or it permanently demotes the memory so the agent stops relying on it. In autonomous systems, unmanaged memory is a liability that actively degrades the agent's intelligence over time. Memory poisoning involves the deliberate introduction of false information into the system, whether through an AI hallucination that gets saved as a learned truth, or a malicious user feeding in bad data to affect future sessions. You block this with provenance tracking. An incoming data node is scanned, revealing its source, confidence level, and reasoning chain. Before accepting it, the system compares its metadata against trusted sources. If it contradicts a higher confidence fact, the system rejects it. The fifth failure mode targets the model's logic, runaway agent loops. Because the model decides when to stop, it can trap itself in an infinite cycle, repeatedly calling the same tool or endlessly refining an answer. Breaking these loops requires 3 hard boundaries. First, hard iteration caps, typically limiting the agent to 10 to 25 tool calls per turn. Second, deterministic loop detection that breaks the cycle if the exact same arguments are passed twice. And third, strict financial budget guards to cap the maximum spend per request. To catch these vulnerabilities before they manifest, you run periodic health checks. You test the agent with known good inputs and track retrieval precision over time, so degradation becomes visible early. Granting a large language model autonomy without establishing strict deterministic iteration boundaries leads to operational and financial self-destruction. Moving from state management to security, the challenge scales up, data, or manipulate other agents to act at scale. This requires a structural shift. Every single agent, tool, and service must be treated as a non-human identity, or NHI, receiving its own scoped identity badge with localized connection lines. These NHIs operate on strictly scoped permissions. A code generation agent gets clearance to read repositories, but is physically isolated from the billing infrastructure. This enforces a zero-trust architecture. Even inside your network, agents do not automatically trust. Every agent-to-agent communication requires valid authentication tokens and clearance levels. Securing the network edge is no longer sufficient. In an autonomous network, the default operational posture must be to verify every interaction. To protect a zero-trust network, use a 6-layer defense and depth model. Watch how concentric rings progressively isolate the core agent. Layer 1 is input validation. It neutralizes prompt injection attempts before they reach the model. Layer 2 provides context isolation. Classification tags ensure agents retrieve information strictly within designated scopes. Layer 3 is tool permission gating. It restricts agents from calling unauthorized APIs and databases. Layer 4 is output scrubbing middleware. This acts as the last defense, scanning outputs for leaked secrets, personal data, and internal IDs. Layer 5 maintains the audit trail. Every decision, tool call, and memory access is immutably logged. Layer 6 is human oversight. For high-stakes actions, the system enforces pauses for manual approval. True enterprise AI leverages automation to handle routine operations, but relies on multi-layered friction to prevent catastrophic errors. Let's trace an active incident. A compromised user session sends a complex, malicious payload into the production environment. The payload executes its first attack vector. It attempts to inject a hallucinated fact directly into the agent's memory store to poison future interactions. Provenance tracking catches it. The system checks the source, flags the update as low confidence, and instantly quarantines the data. The payload pivots. It attempts to bypass its assigned scope and force the agent to execute a direct database write command. Layer 3 tool gating recognizes the unauthorized API call and instantly rejects the request. Cornered, the payload attempts its final attack. It tries to force the agent into an infinite recursion loop, intending to crash the process and extract internal credentials from the resulting error message. Iteration limits kill the loop at exactly 25 cycles, and before the crash log is returned, Layer 4 output scrubbing strips the exposed API keys from the error text. The system survived because it anticipated these degradation modes and enforced a zero-trust, non-human identity architecture. The difference between a brittle toy and an enterprise product is an architecture that expects deterministic failure and is engineered to neutralize it.